Hi everyone, and welcome back to my class. And it's a pleasure to have you here today. In this lesson, we'll be solving three examples on work transfer. So grab your notebook, relax, and let's dive right into learning some new and exciting things today. Example 1. A balloon which is initially collapsed and flat is slowly filled with hydrogen at 400 kilopascal so as to form into a sphere of radius 2 meter. Determine the work done by the gas in the balloon during the filling process. Solution. Step 1. Given data. Pressure of 400 kilopascal and radius, the outer radius R2 given as 2 meter. R1 is taken as 0 as the balloon is initially flat. The next step is to define unknown. Find the work done during the filling process is to be determined. The next step, assumptions. Assumption 1, it is a quasi-static process. That is a slow process. Assumption 2, the balloon is filled with hydrogen at a constant pressure. Assumption 3, the initial volume is neglected as R1 is 0. Assumption 4, the gas is modeled as an ideal gas. Assumption 5, no heat transfer during the process. Step 4 is schematic. At this point, we have radius R1, which is taken as 0. Then at this point, its diameter is taken as D1. And at this point, we have D2, which is taken as 4 meter. And its radius is taken as 2 meter. Step 5, the governing laws and governing equations. The governing law is first law of thermodynamics, and the governing equation is given as integral P dV. Analysis. Now we want to simplify the problem by breaking it down. So the work done, which is given as integral P dV. Now, if you look at the question, there is a particular shape that we are talking about. The shape of the balloon takes the shape of that of a sphere. And we know that the volume of a sphere is given as, the volume of a sphere is given as 4 over 3 pi r cube. Now, the work done becomes P into bracket volume V2 minus volume V1, which is the same thing as P into bracket V2 becomes 4 over 3 pi r squared 3 minus 4 over 3 pi r1 cube. Now, from our assumption, we notice that the initial radius is 0 as the volume becomes negligible in this case. So our final mathematical expression becomes P multiplied by 4 over 3 pi r squared raised to the power of 3. Now, inserting the given data into this equation, the pressure is given as 400 kilopascal. So 400 multiplied by 4 over 3 multiplied by pi is 22 over 7, then multiplied by radius, the outer radius, which is given as 2 raised to the power of 3. So by the time you punch your calculator, the final answer becomes 13405, 13405.9 kilojoule, which is also equivalent to 13.41 megajoule. This is the work done during the process. Let's move to example 2. Solution. Step 1. Given data. Initial pressure P1 is 80 kPa, which is the same thing as 80,000 Pascal. Initial volume V1 is given as 0.1 meter cube. The final pressure P2 is given as 0.4 megapascal, which is the same thing as 400,000 Pascal. And the final volume, V2, is given as 0.03 meter cube. The next step is to define the unknown. Find the work done by the gas system is to be determined. The next step, assumptions or engineering model. The first engineering model is it is a quasi-static process. The second assumption, the gas is modeled as an ideal gas. The third assumption, the boundary work is considered. And here, the change in kinetic energy and change in potential energy are neglected. Assumption 4. The process is described using PVN equals to C. The next step is schematic. As this is a piston cylinder arrangement, for the first one, 800 kPa, and the volume is 0.1 meter cube, and P2 0.4 MPa, and the volume at this level is 0.03 meter cube. The governing equation PVN equals to C, then W equals to C into brackets V2 raised to the power of minus n plus 1 minus V1 raised to the power of minus n plus 1 divided by minus n plus 1. Analysis. The first thing we are going to do now is to determine the polytropic index before we can come back to the work done that we are asked to determine. Going by this relation, P1, generalizing it becomes P1 V1 raised to the power of n equals to P2 V2 raised to the power of n. Therefore, P1 divided by P2 equals to V2 divided by V1 raised to the power of n. Inserting P1, P2 values, we have 80 kPa divided by 400 kPa, which is the same thing as V2 value is 0.03 meter cube divided by 0.1 meter cube, all raised to the power of n. kPa cancel kPa, meter cube cancel meter cube. 40 goes in this. 8 divided by 40, that's 1 over 5. Then 1 over 5, that's 0.2, which is the same thing as 0.3 raised to the power of n. So you add logarithm to base e to the left side and the right side of the equation. So therefore we have ln 0.2 equals to ln 0.3 raised to the power of n. So n becomes ln 0.2 divided by ln 0.3, and the value becomes 1.34. That is the value of n. Now we have gotten the value of n. V1 is known and V2 is known. Another unknown value is C. So we need to calculate for the value of C. And C is defined as C equals to P1 V1 raised to the power of n, or P2 V2 raised to the power of n. Whichever one that you want to make use of out of the two equations is generally accepted. Now we are adopting C to be equals to P1 V1 raised to the power of n. So inserting the value, P1 is 80,000 multiplied by V1. V1 value is 0.1 raised to the power of the polytropic index, which is calculated as 1.34. And the value becomes 3656.71. That is the value of C. Now going back to the governing equation, which is given as W equals to C raised to the power of all this, then we substitute all the given values that we have calculated for and the one that are given in the question into this equation. Now W becomes C is calculated as 3656.71 bracket open. V2 in the question is given as 0.03 raised to the power of minus n, which is 1.34 plus 1 minus V1 0.1 raised to the power of polytropic index minus 1.34 plus 1. Everything divided by minus 1.34 plus 1. So by the time you punch your calculator, the value becomes minus 11,901 minus 11,901.5 joule, which is also expressed as minus 11.9 kilojoule. So that is the work done during the process. The negative sign shows that the work done is done from the surrounding to the system. Now the next work example is example 3. Example 3. A system of volume V contains mass m of gas at pressure P and temperature T. The macroscopic properties of the system obey the following relationship: P plus A over square root of V square then open bracket, V square minus V square bracket close equals to MRT, where A, B, and R are constants. A. Obtain an expression for the displacement work done by the gas during a constant temperature expansion from volume V1 to volume V2. B. Determine the work done by a system which contains 8 kg of this gas expanding from 3 meter cube to 8 meter cube at a temperature of 27 degrees centigrade. Use the values A equals to 12.5 times 10 raised to the power of 3, B equals to 2.09 times 10 raised to the power of minus 2 meter square, and R equals to 278 joule per kilogram. Solution. The data given as step 1, data given, the mass of gas M, which is 8 kg, volume V 1, 3 meter cube, and volume V2 8 meter cube. At a constant temperature, T1 equals to T2, which is the same thing as T, which is 270 degrees Celsius. Converted to Kelvin, we have it as 300 Kelvin. Then the constant values, A is given as 12.5 times 10 raised to the power of 3 Nm4. B equals to 2.09 times 10 raised to the power of minus 2 meter square, and R is given as 278 joule per kilogram Kelvin. Step 2, find. Obtain an expression for the displacement work done. Obtain an expression for the work done. Expression for the work done. And 2, we are asked to determine the work done during the process and determine the work done during the process. Step 3, assumptions or engineering model. Assumption 1, it is a quasi-static process. Quasi-static process. That is, the expansion occurs slowly. Assumption 2, the gas is modeled. The gas is modeled as a real gas. Assumption 3, the temperature is constant. Assumption 3, the temperature is constant. Assumption 4, the change in kinetic energy and change in potential energy are ignored. Assumption 5, frictionless effect is ignored. Assumption 5, frictionless effect is ignored. Governing equation. That is what we are asked to obtain from the question, so which is unknown in this case. Analysis. The work done in a piston cylinder arrangement is given as integral P dV, changing from state 1 to state 2. The relationship of the real gas is given as P plus A over square root of V raised to the power of 3 into brackets V square minus B square equals to MRT. This first one, let's name it as equation 1. We make P the subject of the formula in this case. P equals to MRT divided by V square minus B square minus A over square root of V raised to the power of 3. Name this as equation 2. Substitute P in equation 2 into equation 1. So the work done becomes integral P, which is MRT over V square minus B square minus A over square root of V raised to the power of 3 dV, which is the same thing as MRT, bring it out, integral 1 to 2, 1 over V square minus B square dV minus integral A 1 over V raised to the power of 3 over 2 dV. Now, integrating this expression, we have it as W equals to MRT ln V minus B divided by V plus B. As for state 1 and 2, plus 2A divided by square root of V at state 1 and 2. Now, in the first case, we applied integration by parts. That is why we have this expression. And the second case, we applied the direct integration. Now, substituting the limit 1 and 2 into this equation, the final expression becomes MRT ln V2 minus B divided by V2 plus B divided by V1 minus B over V1 plus B plus 2A is common in this case. Open the bracket, 1 over square root of V2 minus 1 over square root of V1. This is the work done during the whole process, and it is equivalent to the governing equation that we are going to be using to determine the data given in the question. Now, we are going to substitute all the values that were given in the question into this expression. We can name it equation 3 into equation 3. Now, let's insert values. W equals to the mass 8 kg multiplied by the gas constant 278 multiplied by the temperature 300 times ln V2 is given as 8 minus B is given as 2.09 times 10 raised to the power of minus 2 divided by V2 8 plus 2.09 times 10 raised to the power of minus 2. Divided by V1 is given as 3 minus 2.09 times 10 raised to the power of minus 2 divided by 3 plus 2.09 times 10 raised to the power of minus 2 plus 2. The value of A is given as 12 points times 12.5 times 10 raised to the power of minus 3. Open a bracket, 1 over square root of V square. V2 is given as 8 minus 1 over square root of V1, which is given as 3. By the time you punch your calculator, the final result becomes W equals to 129,552.9 joule, which is also the same thing as 129.6 kilojoule. We have come to the end of today's class. Thank you for listening and watching. If you have any question, drop it in the comment section, and please don't forget to like, comment, share and subscribe for more videos.